Okay, so starting part B of homework 3, we are looking at a column, essentially a distillation column that we just derived earlier. Um, and this has a total condenser, 2 equilibrium tray stages between the condenser and the feed stage, and 3 equilibrium tray stages between the feed and reboiler. Before I go ahead and get into the rest of this, let's go and do that. So let's go back into Colab. So yeah, before we do that, we imported a few things, solve IVP, so we can essentially solve our problem, our equation when we need it to. Importing numpy as MP. We're going to be defining MP in this code as we always do, and importing poly dot subplots. And we're going to be making quite a few figures today. All right, so going ahead and listing out the stages, we kind of always start at stage 0, and essentially that's what we're going to do in Colab 2. And before our feed stage, it did say we have 2 equilibrium stages between the condenser and the feed stage. Let's go ahead and label that. So number 1, number 2, and we have our third stage, and this is our feed stage, essentially. Okay. And one thing we can do is this is our rectifying stage before our feed stage. So we're going to denote it as this NR minus 1. And it also said we have 3 equilibrium stages between the feed and the reboiler. So we can kind of add 3 stages, 4, 5, and 6, which is in between our reboiler, and our stage 7 is essentially going to be our reboiler. All right. We can also denote this by our rectifying and stripping stages. So this can essentially make more sense. This is where stripping comes into play. So we're just going to note this by ns plus 1, 1. And we have our fifth stage. We have our sixth stage. We can do something with this. This will be our rectifying plus our stripping minus 1. And then essentially our reboiler is going to be a combination of just both. So NR plus NS, our rectifying stage and our stripping stage. All right. So now that we've defined this, we can also define two things. Want to define how many stages our rectifying or stripping as. So we're going to denote these both as NR and NS. And this is going to be equal to okay, so our rectifying is going to be 3. Just do this. And our stripping is going to be 4 stages, as you can see here. 1, 2, 3, 4. 1, 2, 3. So 4 stages. Okay. All right, now that we've defined that, we can move on and go ahead and define some of the kind of inputs that or initial conditions that we're going to eventually use essentially to kind of first create our distillation column and show this kind of time loop that goes from 25 to 75. But let's go ahead and define. We have feed equals 1.5, z our combination of feed equals 0.4. Let's go ahead and start with those things. We also have our holdups that we can kind of identify, as well as our distillates and our reflux ratio. Let's go ahead, our relative volatility and our reflux ratio as well, which is 2. Relative volatility is also 2. Let's go ahead and start that. So our feed are just going to be equal to 1.5. And this is going to be in units of mole per second. And we also have, again, our Z, which is 0.4. We have our quality, which is 1. We have our reflux ratio. This is 2. And we have, let's go back to this. We have our distillate, which is equal to our feed divided by 2. And we have our relative volatility, which is also 2. We're going to just denote this as 2. Going this down so I don't forget what alpha is, relative volatility. And we're also going to want to define some of our holdups. So our stage holdup, our condenser holdup, our feed holdup, and our reboiler holdup. Let's go ahead and do that. our stage hold up. We're going to do this as stage underscore hold up. This is going to be equal to 0.5. And we have our feed stage hold up. So feed stage underscore hold up. This will be 0.5 as well. And we have our condenser hold up. And this is 1. And we also have our reboiler hold up, which is 1 as well. Okay. So we can go ahead and move on from here. Let's go ahead and shift into this. Oh. Okay, shift into this. Looks good so far. All right, so you want to go ahead and define our hold up, which is essentially the liquid in each and every one of our stages. So we're going to denote this as M underscore hold up, and we're going to be using our np.r arrays. We're essentially kind of creating an array, and we're going to put this back into our m not arrays that we'll define in just a second. But our m hold up is going to be np.r, and this is going to be for our we're looking essentially at our stages and essentially looking at all of these stages. So we're going to start with our condenser. All right, always start with our condenser essentially. So condenser hold up. So starting with our condenser hold up, this will be where we start initially. Then we're going to create another np.r, and this time we're going to be I believe looking at, let's see, gonna go ahead and pause this. Okay, so back, this will be actually np.full, my mistake. And what we'll be using here is our stage hold up. So it'll be np.full, and we're gonna be using our starting at our second stage, so nr minus 1 that I defined up there. So nr minus 1, comma, and then we'll be looking at our stage hold up. Comma stage hold up, and then we'll be combining this, and we're going to be looking at our feed stage hold up now that we've done our kind of stage hold up coming off of our second stage there. So feed stage hold up, go ahead and press this, feed stage hold up, and then we're going to be looking np.r again, underscore, and then we're going to be looking at our reboiler hold up. So reboiler, let me go fix this. I messed that up. Reboiler score. I feel like I've messed something up. It's not going ahead and doing that. Feed stage hold up. We have MPR. We're looking at our reboiler. Ending off with our reboiler hold up. Let's go ahead and just finish that out. Hmm. Go ahead and run this all. Okay, not too sure what happened here, but let's go ahead and we know that we have to initialize and define a hold up that we kind of derived in the other part of our homework. Let's go ahead and move on from here. So we're going to want to define our where. That's kind of what we were working on before. That was kind of coming off of that second stage. We're just going to define this as 1, as given in the problem statement. And then we have our m not, which is going to be equal to m underscore hold up. And then this will be multiplied by 1.05. And then we're looking at our m not and giving it an array. So just array at 0. And then this will be equal to r plus 1 plus 1. And this will be multiplied by our t that we defined just above there. And this will then be divided by our where. I'm going to give this another comma. And then this will be to the 2/3, so 2 divided by third, and then we'll add the condenser hold up here. So add condenser hold up there. Okay, so I think we got too many parentheses here. Okay. Because yeah, so we don't have this yet defined, but we know that. So let's go ahead and start this next code. Okay, all right. So we're back and we did have this error. I went ahead and moved on, but realized my mistake. Let's go ahead and erase this. So we're actually looking at a mp.full, and we're going to be looking at, if you go up here, again, we're looking at our stripping, so ns minus 1, and then we're looking at our stage hold up here, and then put a comma here, and then this will be our reboiler underscore hold up. All right, so that should look good. Hopefully, there you go. Okay, so that should fix that. Before we go ahead and shift enter this, we have our initial composition that will feed our stages essentially. This will be defined as x naught equal to np.full underscore like, and then yep, so this will be at m naught and 2. So shift into this. M naught and Z, which is essentially our mixture. Shift into this. And we're going to want to go ahead and define our ramp. This is essentially what we're going to be creating. And this is going to be from our ramp at T, and then it'll be from 2 points, so A and B. And we want to give it kind of like an if-then statement, if this is greater, if this is less than. And so we're going to be saying that if T is less than A, we're going to return 0. And we're going to be saying if T is greater than B, T is greater than B, we are going to return 1. And then we're also going to return, in this case, T minus A divided by B minus A. Right? It looks good. So we're going to want to go ahead and finally make our subplot. So there's a few things we need to kind of define. We're going to start by kind of creating our subplot. So fig equals make underscore subplots. And then we're going to go ahead and make our time plot. So essentially we're doing this from 0 to 100. We just want to give it kind of a time from this point to this point. So our t plot is going to be equal to mp dot linspace from 0 to 100. Right. So from this point, we can go ahead and make our y plots, and then this will be equal to, well, it's from 0, it was from t to 25 to 75. That's kind of what we wanted to, where we wanted to kind of break off and give it our ramps. So we're going to be seeing that 2 times ramp t to 25 to 75, and then plus one for t and t plot. There you go. Looks good. And then we're just gonna kind of want to initialize these and create it with our, let's go ahead and enter this fig dot add underscore scatter. Essentially just make our time plot from our x and y. So x is going to be equal to our t plot, and our y is going to be equal to our y plot. Okay, so perfect. So we have our jump from 25, and then we go ahead and at 75, it kind of comes back down and stays constant. So essentially, this is our ramp from 25 to 75 that we just initialized right here on our T line, our time plot. We have this ramp. Cool, so we can go ahead and move forward. All right, so now that we have that, we essentially now want to set up our differential equation. So that's gonna be kind of initializing several values, defining some vectors, and then kind of plugging in what we did from the last part. But before we get into that, let's go ahead with defining our right-hand side. And defining our right-hand side, we're gonna define our t value and v, which is our vector, as well as our reflux ratio. And this will be denoted as you can see here, reflux ratio function. Okay. We also want to set this value of our reflux ratio. So we're going to set it as R, and our R, let's go ahead and do this. R is going to be equal to this reflux ratio function as a function of T. So reflux ratio as a function of T. Let's go ahead and write that out. Ratio function as a function of t. All right, so that looks good. Now what we can do is we want to set up the ramp. Essentially, we're setting up a distillate that is based off of that ramp that we created. And we're going to be doing it from 50 to 100. And that's going to also be multiplied by our feed divided by 2. Let's go ahead and write that out. So D is going to be equal to our ramp. And then this ramp is going to be from T to 50 to 100. And then this will be multiplied by our feed divided by 2. Divided by 2, divided by Z. Sorry, might have. Okay, then now that we have our distillate set up based off of our ramp, we can set two values that are essentially going to be equal to our vectors. So we have M and X, and this is going to be equal to, we're going to essentially be splitting up these values. So we're splitting up these values of M and X into our vector and splitting up and pretty much splitting it up into 2 is what it's doing. So we can have our vector and we can have 2 right here. Okay, so now what we want to do is we want to set up our vapor composition. We've done this before, and it's essentially just going to be our alpha, so that relative volatility kind of constant that we kind of defined up there. As you can see, yep, we do have it defined as 2, our relative volatility. So our alpha is going to be then multiplied by x, and then this is going to be divided by our 1. This is going to be divided by 1 minus x, again, then plus our alpha, and then multiplied by x. Okay. So now what we want to do is we want to essentially set up our differential equations. And before we do that, we want to initialize a few different kind of derivatives, and that's going to be of our composition. It's going to be a derivative of our composition, vapor, and our moles. Okay, so we want to set up those 3 functions before we can actually set up those differential equations, because we want to initialize these values before we actually introduce them. So starting with just the derivative of our moles, which is just essentially dm, we're going to be setting up NP zeros like, and this is going to essentially pull this function of m. So now that we have this, we can set up. I'm going to explain in just a second what this MP zeros actually does. But then we have our DMX, which is essentially our composition, mole composition, and this will again be MP dot zeros underscore like, and we have our DM. We can just denote this one just as V, which will be equal to our MP dot zeros underscore like as a function of M. And what we can do now is set up our liquid flow rate. So this is, as you can see, we're going to introduce this equation that sorry, I didn't put in here, but we're going to introduce this hold up equation. So when overflow, our liquid flows via overflow at a rate of 1.0 times our hold up minus hold up not to the power of 1.5. So we're going to be introducing this equation here. Let's go back and set this up. So we're going to use our np.where function, np.where, and then this will be from m less than our m underscore hold up. Yep. And then this will be from 0. And then we can introduce this our where so that we kind of what we drew out in our last part of our video. And this will be multiplied by that equation that we just looked at, which is our m minus m underscore hold up. And then this will be to the 1.5 power. So we can denote this by two of these and then 1.5 and finally close this out. Okay. So this L naught, so pulling this first value, what we want to do is pull this first value again of that liquid flow rate. So introducing this, and then this is going to be equal to R times D. Okay, essentially just a balance of these of our reflux ratio function and our distillate that we just kind of labeled as our new distillate based off of our ramp. Okay, so kind of last thing we want to initialize here again is our VREC, so which is essentially the vapor in the rectifying section, and we're just going to denote this as VREC, and then this is going to be equal to what we just introduced up here, so our L naught, pulling out that first value, and this is going to be added to our D that we just kind of defined up above. Let's go Control Shift Enter that. Okay, so starting where we left off, we initialize this VREC for a rectifying stage, and we're gonna go ahead and we're gonna input some initial values, and then we're gonna go ahead and insert that differential equation that we derived in the earlier part. Let's go ahead and do that. Okay, so starting with our V, we're initializing this at our 1, and this is going to be to our NR plus 1. So that stage up here. Right, yep, see, so our NR plus 1 stage after our feed stage. So be after before a reboiler. So NR plus 1, and we're going to close this, and then this is going to be equal to our VREC. So just to kind of initialize this, see what we're looking at. We're looking at our vapor stripping flow, vapor flow for stripping or stripping. Okay, so now we're gonna want to do this for our stripping. So this is gonna be our V. So we're initializing this again at our V, and it's gonna be again our NR plus 1. So NR plus 1, and then we're going to close this. So it's going to be pretty much capturing all these values at the end of our array. And this is going to be equal to VREC, but because we're working on our stripping, this is going to be subtracted by our feed, and this is going to be multiplied by our quality, but our 1 minus our quality. So that's going to be our stripping. So we can go ahead and write something down for that. So, sorry, this is for our rectifying, messed that up. And then this will be for our stripping, vapor flow or stripping. Okay, so now we can go ahead and determine some of those differential equations that we evaluated in the other part and insert those into Colab here. So we're looking at dm is what we're kind of defining it as, and this is going to be from 1 to -1, and then this is going to be equal to our liquid, so L, and then this is going to be at our semicolon -2. Yeah, so it's gonna kind of um capture everything from the left-hand side, all the values, and do it all the way up into -2. So that's pretty much when we kind of initialize a semicolon, but don't give it a value before or after. So our L, and that's going to be minus L for 1 to -1 here. So just ensuring that equation that we worked on previously. It's going to be plus our vapor. This is going to be 2 semicolon, and then we're going to be subtracting by our vapor again, and then this will be from 1 to -1. Okay. All right, so now that we have this, we can go ahead and kind of define this differential equation in terms of our NR, the that rectifying stage right before our boilers. So let's do that by inserting our NR here, and then this will be we're going to be using our plus equals, so plus equals, and this will be equal to our feed. Yeah, so starting out, we're going to do this array initialize at our set of 0. So we can input our 0 value here and define this array. And this is going to be equal to V at our value of 1. And then this will be minus our liquid at our value of 0 minus RD, our distillate. Okay. So now that we've done this at 0, we can do it at -1. This is going to be dm -1. Let's go ahead and close this. This is going to be equal to liquid -2. And then this is going to be minus our vapor at -1 minus our liquid at -1. Okay, perfect. Okay, so now that we've done this, we can okay, so we can now do this uh for what we define and when we were deriving, and this will be for DMX, which is essentially looking at our change in our compositions, and the kind of the steps that will go through this is very similar to what we did previously. However, we're going to be multiplying it by our liquid or vapor compositions. So let's go ahead and define our value for this, which is just DMX. DMX, and then that's going to be from again 1 to -1, same what we did before. So 1 to -1, and then this will be equal. Again, I mentioned how we have to multiply what we kind of had previously and what we derived from the earlier parts by our composition. So that's going to be starting with X, and this is going to be from semicolon -2. And we're then going to multiply this by our liquid, and then this will be from semicolon -2. Right. Yep, that looks good. And then we're going to subtract this by X, and then this will be from 1 to -1. And then again, this is going to be multiplied by our liquid from 1 to -1. I'm going to go ahead and close that. And then this is going to be added by our vapor in this case again, and this will be from 2 to 2 and then semicolon to the end of our array. And then this will be multiplied by our vapor. Again, we're looking at our vapor composition. So now we're looking at our vapor flow. And then this will be from 2 to the end of our array, right? So kind of similar to what we're working on before. And then this will be subtracted by y, which is our vapor composition. And then this will be from 1 to -1. Yep, 1 to -1, which will be multiplied by our vapor from 1 to -1. Yep. Okay, so that looks good. And then again, we want to initialize this for NR that we did earlier. So DMX for NR, and which will be similar to what we did for our feed, except we're going to be multiplying it by 2. So DMX NR is going to be plus equal to 2 times our feed. Okay, so that looks good. And then we can go ahead and initialize these values again for our 0 and -1. So 0 is this will be equal to y, our vapor composition at our value of 1, at our value of 1 multiplied by our vapor, again at our value, oh, again at our value of 1. And then this will be subtracted by x at our value of 0, and then multiplied by our liquid at our value of 0. Okay, so that looks good. And then we're going to be subtracting this by our x at our value of 0. Again, we're looking at DMX at 0, the change of our liquid composition. And then this will be multiplied by x at our 0 will be multiplied by our distillate. We can go ahead and multiply by that by our distillate. Okay, so now we can do this for -1. So yeah, it's similar to what we did for our DM to DMX, but just more complicated, I would say. So DMX at -1 is going to be equal to x at -2. And then this will be multiplied by our liquid at -2 minus y. Yep, minus y at -1. Oh, minus y at -1 times our vapor at -1 minus times our vapor at -1. Okay, so this is going to be subtracted by our x at -1 multiplied by our liquid again at -1. Okay. All right, so now that we have that initialized, what we want to go ahead and do is kind of define what dx is in this case. So dx is going to be equal, it's kind of going to be correlated to our dm and dx. So it's going to be our dmx minus our x times our dm. And then this is going to be divided by n. Okay. So we can go ahead and return this value. So as it says here, and return mp.r underscore, and this will be for dm and dx. Okay, cool. All right, so we can go ahead and move on to our next part of code. Okay, so what we want to be doing now is kind of configuring our plots. So we're going to want to go ahead and set up some values so we can go ahead and create that for this part B. So let's go ahead and start with creating Tn, and we're just going to start by giving it a value of 300. We might go ahead and change that. Very may well do. So we're going to go ahead and set up our solve function, solve IVP. So we're going to set res equal to solve underscore IVP. And this is going to be for our right-hand side from 0 to Tn that we just defined right above. And then this is going to be for our values of np.r underscore. This will be for our values of m0 and x0 that we define. So we go ahead and kind of go ahead and define that. We can set up our method, which will be equal to redow. So just stating some values for our subplots that we usually do. So setting up our method, we can go ahead and set up our dense underscore output, and we can equal that to true. And then we can go ahead and set up our args. So we did that in some parts, and we're going to be doing it for this one. And our args is going to be equal to our lambda. So set up our lambda from t to 2, and that's going to be configured by a period as well as a comma. So just some kind of minor details to be aware of. Yeah, so that should be good. Let's go ahead and shift enter that. Oh, I don't want to shift enter it. A lot of stuff might not be kind of defined. So just go ahead and run all of this. Okay, that's cool. All right, so let's go ahead and start with our next line of code. We're going to be setting up our t plot. So that's going to be equal to np dot linspace. And that's going to be from 0 to tn to 300, or just do that to 100. Sorry, I was thinking about tn, which was that set at 300. So our t plot is going to be equal to np dot linspace. We're going to go ahead and configure a subplot. So we're going to do big equals make underscore subplots, and this will just be rows, our rows equal to 1 and our columns equal to 2. Okay, so now that we have that, we want to go ahead and set up our m and x's that we kind of defined and evaluated earlier. We want to set this up and put it eventually put this up into a enumerate is how you pronounce it. Enumerate. Sorry. Yeah, there you go. But let's go ahead and kind of define these. So m's and our x's. So we never define them, but we're going to be defining them. So our m's and x's are going to be equal to np dot splits. And then this is going to be our res1 dot solve from our t plot. And then this is going to be at 2. Okay, right. So send that at 2, and then we're going to set our axis equal to 0. Okay. All right. So we can go ahead and set up our for loop. So for I, m and enumerate. Yep. So for I and enumerate. Yeah, so we're going to set up our m's here, and let's go ahead and close this. All right, so now that we have that for loop set up, we can add a scatter plot. So fig that add underscore scatter, and we can set our x equal to our t plot and our y equal to m that we just defined. And then we can set up our rows. So row equal to 1, column equal to 1 in this case. I'm going to be setting up a name. So in this case, it's going to be f dot moles. And then we're going to be setting up this thing right here, which is our I. And then, yep, so that looks good. Let's go ahead and change this. All right, so let's go ahead and add another for loop here. So we're going to say for I, x, and enumerate, and then we can do our x's in this case. So essentially the same thing. Let's move this here so we have it. So fig, there you go. Okay, so we just want to go ahead and change some things here. So our x is going to be equal, yeah, that looks good. Y is going to be equal to 1, row equals 1, column equals 2. And then this f, our name for this um, is going to be our mole fraction here. So let's go ahead and change that. Okay, that looks good. And then we can go ahead and finally just update our layout and create our subplot. So fig.update underscore layouts. Our width is going to be equal to 800. Our height is going to be equal to 400. And then we can go ahead and set our template equal to plotly underscore dark. Okay. Press one is not. Okay, so decided so realize the mistake I made. I had this value right here defined as res1. However, when I defined that this term right here, res equals solve underscore IVP, I never stated it as res1. So that kind of messed up the code when we were doing it. So now that we have our res um fixed, we can go ahead and actually get our graph, and this looks correct. We have our moles on our left-hand side and our mole fractions on our right-hand side. I can see that we have various different kind of entities here. We have this constant line right here. If you can go ahead and look at the different mole lines here to see how they differ. Let's go ahead and erase some of them so we can kind of see what we're looking at here. Yeah, but this is kind of, you can see how the lines differ based off of our compositions. And we see that this goes from 0 to the 300. We have all of our mole fractions here on the right. Let me go ahead and pull up the problem statement. Sorry, give me a second. So as you can see here from the problem statement, we were kind of, so we were told based off of our initial condenser holdup to provide a flow rate of a flow half of the feed at a reflux ratio of 2, which we define at a distillate flow from 50 to 100 seconds of the simulation. And we're simulating this response over the first 300 seconds, as you can see here. So it looks good. What we want to do now at this point is move on, and we want to kind of define this graph that we just kind of did, and do it based off of our Mikhail Cape Deal diagram. Still all working on part B. We're just kind of doing this based off of a different version, I would say, but this will differ. And we'll see how we kind of change those initial values on part C to see how that kind of differs. Okay, so defining this, we want to go ahead and start by creating our X plot. So we're going to say that our X plot is going to be equal to our linspace, and we're going to be giving it our initial values from 0 to 1 to 100 in this case. And then what we're gonna do is we're gonna kind of define another set of our x's. I know there's a lot of x's and y's that we're dealing with here, but in this case, we're gonna be setting this equal to xss just to kind of differ from what we defined earlier as x and s x's. So our x's in this case are going to be equal to our x's, and this array is going to be from all those values on our left-hand side to -1. Go ahead and do that. And now that we have that defined, we want to go ahead and define our y's. So our y's are going to be equal to our y, I believe it's y times alpha times our x's. There you go. Times our x's, and this is going to be divided by 1 minus our x's that we just defined earlier. And then this is going to be again added to our alpha times our xss that we just defined, right? So now that we have this, we want to now define our steps. So our X steps and our Y steps that we'll see in our graph that we're going to create. So that's going to be defined as X steps is going to be equal to NP dot R underscore in our brackets. This X is going to be defined at our initial value of 0. And then this is going to be at NP dot repeat. And then this is going to be from our X's to 1 to -1. Okay, so I believe you got that all correct. Nope. So let's fix that right here. Okay, we have that now from our ones to ones, and this is going to be at 2, and then we can, there you go. No, so we're not done yet. We have this at 2, and we want to go ahead and say that our X is at -1. At -1. Okay, there you go. So now that we have this, we want to go ahead and define our Y steps. So this is going to be equal to NP dot repeat at our Ys. Again, we're working at our Y steps. So we're going to be working on our Ys, YSS in this case. And this is going to be at 1 to all those values on our right-hand side. And then this at, again, 2. Okay, now that we have our X steps and Y steps created, as well as our X's and Y's, we can go ahead and create our subplots. So we're going to say that fig equals make underscore subplots. And from this, we want to go ahead and add all of our scatters. So going ahead and doing that, we'll do fig dot add underscore scatter. And this is going to be equal to X equals 0 to 1. Y is going to be equal to the same thing. Y is going to be equal to 0 to 1. And our mode is going to be equal to lines. And our line color, we can just go ahead and give it a color. Line color is going to be equal to, in this case, we're just going to do gray. Okay, now that we have that, we can go ahead and define our X plots as well as our X steps and Y steps. Let's go ahead and define our X plots as well as our Y plots that will have to be kind of reconfigured and evaluated in a different way. So fig dot add underscore scatter. X is going to be equal to our X plot, and our Y in this case is going to be a little different. It's going to be equal to alpha. It's going to be equal to alpha times our X plots, and this is going to be divided by 1 minus X plot. Yeah. Yeah, it's going to be divided by 1 minus X plot plus our alpha times X plot. So 1 minus X plot plus our alpha, whoops, times our X plot. And we're going to go ahead and again give this a line color. So let's say our line color is going to be equal to red in this case. Okay. So now that we've had this defined, we can go ahead and do it for our X steps and Y steps. So let's go ahead and just, now let's rewrite this. So fig that add. Yeah, so it's kind of what we want. It has mode in here. As our line color. If we do need a line color for this one, but let's go ahead and do that. We have our X equals our X steps, our Y equals our Y steps. We have our mode is equals our lines. Let's go ahead and give this a different color here. So this will be orange in this case. And then we have our fig dot update underscore layouts. Let's go ahead and change these widths right here to 500 for our width and 500 for our height. And one more thing for this, we want to make our legend false. So show legend equals false. Okay. Oh, I knew I messed something up there. Okay, so saw the mistake I made here. This is gonna be y equals not used to that kind of command and when we're coding, but let's go ahead and shift enter. Hopefully, no, that is not a stepwise function. Oh man, something is definitely wrong. That's weird. That's real weird. So let's go ahead and see what mistake we made for this. Okay, so realize the mistake I made. There is actually a comma here. So let's go ahead and hopefully that's what we wanted to. Perfect. So as you can see here, we have our equilibrium curve. We have our stepwise function that we want to see. This kind of comes here and starts at our distillate right here and kind of makes its way down towards our bottoms. This is relatively an example of our McCabe-Thiele diagram in this case, based off of these parameters. But we're going to go ahead and kind of implement the uh, same kind of thought process into our part C and kind of create a McCabe deal diagram based off of that. But we'll go ahead and do that in the next part.